Welcome everybody. So we are going to start talking about the transition to IPv6 for the service provider specifically. So it is a short introduction actually with the principal tools and protocols that are used. We will start with an history of the old protocols, and then we will explain the most important ones. My name is Frederick Bovey, Fred. I'm in the industry for 20 years, in IPv6 for 15, and you can meet me on the internet, drop me an email, and ask me any question if you want. We talk about anything in IPv6 or routing and switching in general. So let's start talking about IPv6. IPv6 is the very first example of protocol I know where so many tools were provided to manage the transition. Actually, in the past, when, for instance, when we moved from SNA to TCP/IP, or from a digital DECnet to TCP/IP, or from NetBIOS to TCP. I mean, any protocols migration, we never need to have any tools to do the transitioning. We just migrate the application, and that was it. And transitioning of a protocol is not so difficult, but for IPv6 since day one, tools were provided to allow a smooth transition with maximum possibilities to make it really easy. So the first tools provided were dual stack and static tunnels. This has permitted to create the 6-bone, which was a experimental IPv6 Internet built over the IPv4 Internet with static tunnels. And at the same time were started NATs and private addresses. Many people are thinking that NAT is a feature of IPv4 and of IP in general, and which is really a feature that was there since day one. And actually NAT is just a workaround to deal with address depletion. And NAT has broken something which was very important in the internet. You know, if a lot of people moved to TCP/IP, it was because of the peer-to-peer nature of TCP/IP. For instance, IBM SNA, they introduced LU62 and APPN, which was the IBM answer to peer-to-peer. And actually, the big driver was peer-to-peer. And NAT broke this peer-to-peer functionality, and with NAT we are actually obliged to run sometimes servers and introduce an hierarchical, no more a peer-to-peer network. So that's something which was introduced in the 90s and which was not something since day one of IPv4. The second generation of protocols are the protocols which have permitted the service providers to develop and to provide IPv6 services. So for the service providers with MPLS backbone, the solution was 6PE and 6VPE. Actually, Cisco started to develop 6PE in the very early 2000s. Why? Actually, it is very simple. MPLS VPN and MPLS was started at the end of the 90s everybody was having its own IP switching technology, and tag switching was the product of Cisco. And many service providers launched tag switching backbone because it was not only for performances, but it was also permitting to add many services like a VPN, for instance, very easily. So it was not possible to tell a customer who was just starting an MPLS IPv4 backbone, Mr. Customer, just let's forget about your brand new backbone because the future is IPv6, and now you must buy and redesign your network to make IPv6 instead of MPLS. So Cisco developed 6PE because 6PE was permitting to start providing IPv6 service on the top of an IPv4 MPLS backbone. The service provider without MPLS, like Free in France, so it is actually Free, which developed a 6RD, which was actually a technology to provide IPv6 service on the top of an IPv4 backbone as well, but without MPLS. At the same time, we tried also to find solution to use the remaining IPv4 public addresses with maximum efficiency. And solution was obvious. NAT was successful for 20 years running at the CPE, so the idea was to run NAT at the service provider backbone, and this time it was not only possible to share an IP address among multiple computers, but among multiple customers. And we have seen many solutions based on CGN to permit this sharing of a public address among multiple customers. Other solutions also were introduced, which was NATPT, to translate IPv6 to IPv4. Actually, NATPT was doing everything, and because it was trying to solve too many problems, it was too heavy and could not do it very efficiently. So it is now deprecated, but it gave birth to NAT64, GNS64, and we will see the use of it. And it is actually currently a solution which is deployed by service providers. What I'm calling the third generation of tools were actually started at the same time than the second generation. Basically, it is the same service, but without stateful NATs. So it is the most popular architecture is A+P. A+P is based currently on protocols like DV and 4RD, and basically they are stateless protocols, so they don't have all the drawbacks of the stateful NATs in the core, and that's why they are very interesting for service providers who were loving NAT when NAT was running at the customer, but they don't like NAT so much if they have to run NAT in their own backbone now. So if we look at the transition history, we can see that we started with the 6-bone running with static tunnels over IPv4 starting in '96, and it actually stopped in 2006. It was a test bed for testing many IPv6 protocols and solutions. The very first protocols which permitted to deploy IPv6 for service providers was 6PE. It is at this time, but I joined also the Cisco IPv6 engineering team, and I started to help the dev testing of 6PE and 6VPE. It is always the best solution for service providers which is running an MPLS backbone and who don't want to upgrade its core to IPv6 immediately, but still wants to provide an IPv6 service. 6RD is the solution for the IPv4 backbone, but without MPLS to provide IPv6 service to customers. Other solutions that we see now are for the service providers who have completed the previous step and are now running an IPv6 core. And if they still have to support IPv4 customer, then they will need a service like DS-Lite, which will permit to connect the IPv4 customer through the IPv6 backbone. And for customers who are IPv6 only and who need to connect IPv4 service, NAT 6.4 is the translation protocol which is currently being deployed and which permits again for IPv6 only network to access IPv4 contents. Below the arrow you can see that a lot of protocols are still testing but not much deployed. And below the blue arrow down is a standardization, and actually you can see when the RFCs were published. So again, the very first step for transitioning to IPv6 was with network address translation, and the NAT 4.4 was really the first one in the 90s with the private addresses. It has permitted to extend the life of IPv4 20 more years with private addresses. But again, IPv4 with NAT is breaking a lot of functionalities of the internet, and many people love NAT, and they cannot imagine a network running without NAT. But NAT was never a feature; it was a workaround. And if it can provide the illusion of security, it is not a security feature. It is at the opposite. It can be a target for those attacks. And really, if we can, IPv6 was also mostly developed to get rid of NATs. NACPT was the first attempt to translate IPv6 to IPv4. It has a lot of the drawbacks of NAT, and it was really a last resort solution. NACPT was trying to solve all the problems. NAT 6.4, NAT 4.6, and all the application layer gateway for DNS, FTP, or everything. So it is now deprecated, but it gave birth to NAT 6.4 and DNS 6.4, which again is very useful for customers who are only running IPv6 but still need to access IPv4 content. And in the same time, we have seen also carrier grade NAT, which is actually NAT running at the service provider backbone, and which permit to share an IPv4 public address among multiple customers. We will see that it looks nice, but it has many drawbacks, and service providers are very cautious, and it is not much deployed currently. So first solution was for transitioning, proposed in '96, was to use static tunnels with dual stack routers. So it permitted to develop the 6-bone, but it was not very scalable, and in no way it was something possible for a service provider to develop to provide a large-scale IPv6 service. So then we have seen automatic tunnels coming up. Automatic tunnels like 624 solve two problems. It solves the problem that the customer don't need to request an IPv6 address because a block of address is reserved for 624. And it also solves the problem that you don't need to configure the IPv4 destination of the tunnel, because the IPv4 destination of the tunnel is derived from the IPv6 prefix. So actually, if you take the example of this address here, 2002 CO46:1, this is a /48 prefix, and it comes from the IPv4 address 192.70.0.1. So 2002 is the reserved block of address for 624, C0 is 192, 46 is 70, 0 is 0, and 1 is 1. So then you got a /48 prefix that you can subnet to configure as many subnets as you need. Basically, you have 16 bits for subnetting, and you can subnet many LAN on your sites. 624 use public relay to access the internet. There is an IPv4 anycast address to access the closest 624 relay, but again it cannot be used by service providers because of this fixed prefix 2002, which is not suitable for a service provider which cannot control the return of the traffic. So a French service provider thought that 624 was not a bad idea, but the problem was the fixed prefix 2002. So they actually customized the stack in 2007 to allow a customized prefix instead of 2002. This way it was possible to deploy a service and to deploy 6RD gateway which permits, or relay, which permit to access the IPv6 internet, and the return path is also controlled because the prefix is unique for the service provider. So you see that we need a CPE, which is a 6RD CPE, and a 6RD border relay to connect to the internet. So basically the 6RD CE needs to know the IPv4 address of the border relay, and when the 6RD CE detects that the remote address is not in the 6RD domain, it forwards the packet to the relay instead of sending it directly to the neighbor in the same domain. So again, it is same principle than 624, but instead of the 2002 prefix, it is a prefix that you can customize for each service provider. After the prefix, which is used by the service provider, you find your customer IPv4 public address, which is going to be used to address a particular customer in the 6RD domain, and then the interface ID. So again, it is exactly the same principle than 624. Only difference is the prefix, which is no more 2002, but a customized prefix which permits to customize a service provider, and for the service provider to implement a relay and control the return traffic back to the customer. So if the destination address is in the same domain, the encapsulation will encapsulate the packet directly to the other customer within the same domain. But if the destination does not match, then the CE is going to forward the packet to the border relay, because it has in its configuration the IPv4 address of the border relay, and the border relay is going to forward the traffic to its IPv6 destination, and it will also receive the traffic coming back and will encapsulate it again in IPv4 to reach the residential gateway using the IPv4 access network of the service provider. So why 6RD is a very good solution and why many customers are using it? Because it is cost effective. Because basically you don't need to have one tunnel for each client, as it was the case for many other technologies which were expensive. With 6RD, it is possible to use a single tunnel to aggregate all customers, and it is very different from a price point of view. It is much, much cheaper than other solutions. For service providers with MPLS, there is still no question. The solution is 6PE or 6VPE, and the beauty of the solution, again, is that it does not require any upgrade of the backbone. And there is no performance degradation. I have been running a lot of tests with 6PE and 6VPE, and we could see that the performance of 6PE and 6VPE were mostly actually the same performance that native IPv6. Maybe the only problem with 6PE and 6VPE is the lack of multicast IPv6 multicast support. And IPv6 multicast is very important. There are already many applications, many radio, for instance, which are using IPv6 multicast, and multicast is not the friend of MPLS. So that's a reason why service providers may migrate quickly to a native backbone. When you have migrated to a native backbone and you still need to connect IPv4 customer, then you need a solution. And currently, I think the best solution is DS-Lite or maybe 4RD. There are pros and cons for DS-Lite or 4RD actually. With DS-Lite, we actually tunnel the traffic to the service provider backbone, and it is only in the service provider backbone that the private address is translated to a public address. So it combines the benefits of carrier grade NAT, allowing to share a public address among multiple customers. It is a nice solution because you start have an IPv6 link with your service provider, and it supports both IPv4 and IPv6 nodes. With IPv4, we will have a large-scale NAT translation. For IPv6, it will be directly connected to the internet. I have this running at home, and I can see my IPv4 nodes running private addresses, but my IPv6 machines are running public global IPv6 addresses. Now, what's happened for customers who are running IPv6 only, but still need to access IPv4 content? Solution is NAT 6.4. Currently, the example I have are T-Mobile, which is a mobile phone operator, and they have started to provide an IPv6 service only, and they are using NAT 6.4 because actually more and more contents are now accessible with IPv6. Google, Facebook, and many other services are now running IPv6. So the T-Mobile people think that the translation will not be needed in many cases, and in most cases the content will be delivered in IPv6 and will not need any translation. The protocol translation is very simple, actually. It is a little bit more complex than this, but here is the principle. So the DNS 6.4 and the NAT 6.4 are no more in the same box as it was the case with NAT-PT. So the client is requesting the IPv6 address for a name. If the DNS 6.4 cannot find an IPv6 address but only IPv4, it is going to translate this IPv4 address to an IPv6 address using the well-known prefix 64FF9B, and then C0 is 192.0.0.22 and 11, so we find C0201, which is actually the IPv4 address coded in IPv6. And then we can start a TCP connection. The traffic is routed to the NAT 6.4 box running normal IPv6 routing, and translation is performed in both directions. NAT 6.4 comes in two flavors. It can be stateful or stateless. In stateless, it is a one-to-one translation. We cannot save IPv4 addresses. In stateful NAT 6.4, actually the same IPv4 address can be used by many IPv6, so we still save IPv4 addresses. Another way to save IPv4 addresses, as I explained at the beginning, is to run NAT in the service provider backbone. So the CPE at the customer is no longer translating a private to a public address. It is a private to private translation. and it is only at the service provider that the private address is translated to a public address. So this way we can share a public IPv4 address among multiple customers, and not only as before with the GPE NAT we were sharing an IPv4 address among multiple computers, but now we can also share the same address among multiple customers. So it looks great and nice, but it also has many problems. First problem is the scalability. So how are you going to manage and do the capacity planning to figure out the resource needed by the LSN? How much memory, what CPU will you need for the LSN to do all translation? Because it is very difficult to figure out how many translation will be needed by the LSN. So two solutions. One solution, no limits, and when the LSN box has no more memory, it is going to crash, which is no good. Other solution, you fix a limit, but when you fix a limit, it means that when the limit is reached, there is no more service, no more access to the internet. So, not really simple choice. It can be a solution in some environments which are very well controlled. For instance, again, in the mobile phone environments, because you may know that a smartphone is going to run a limited amount of connection and will not require a huge number of translations. Also a single point of failure, because if the LSN box reloads, it is all the customers behind the LSN who needs to restart their sessions. So it is not something that we really like to see happen. Another solution is the overlapping of private addresses, because we are using private address at the customer and private address in the link with the service provider. So what's happened if the customer uses the same address than the link used with the service provider? We have overlapping addresses, and we know that IP is not working very well in the presence of duplicate addresses. So it can be a problem. Another problem is when two customers are behind the same NAT box, because the packet will come back to the next customers with a private source address. And usually most firewalls don't like to see a packet coming from the internet with a private source address, and usually it is going to filter out these packets. So this is bad, and one way to avoid this could be to translate all packets, but it means that the LSN will be really loaded, because it will also need translation for the local traffic, which is really a lot. So the double NAT design issues, overlapping addresses or two customers behind the same box are two big problems. And also the problems that we have with any kind of carrier grade NAT solution are scalability and single point of failures, because again it is very difficult to guess how many translation will be needed behind a LSN box. And again, if one box must reboot, it is a lot of customers who will need to restart their session, maybe log in again and restart their application. So in terms of network availability, it is not very good. Alright, so other solutions is DS-Lite. DS-Lite is not so bad solution. It also has the problem of carrier grade NAT, because again, LSN, the translation of private address is done at the service provider backbone. But here, the CPE is not doing NAT, and we are running an IPv6 link with the service provider. So we don't have the problem of overlapping addresses, we still have the problem of we still need to translate the address if we have two customers behind the same LSN, but overlapping duplicate address we don't have. Another solution which can be used instead of DS-Lite is 4RD. 4RD does not make any assumption about NAT. NAT can be running at the CPE, or NAT can be running at the service provider, or NAT can be not running at all if the customer is running public address, but it is not the most common case. So that's also a solution which is an alternate solution to DS-Lite, and which can be a good solution. So you'll find a little bit of pro and cons for 4RD compared to other solutions. This solution was actually also a possibility to avoid the the overlapping addresses, because we have an IPv6 link between the customer and the service provider backbone. But in this case, we need to run NAT46 at the CPE, and so if the CPE is software upgradable, it may not be a big deal, but if you need to replace all the CPE to run NAT46 at the customer, this can be a problem. On the other hand, there is a stateless version of this service, which is called DV or DVPD, and which is very interesting for the service providers. DV and DVPD is currently the base of an architecture which is called A+P. A+P is a very interesting solution because it actually permits to share a public IPv4 address among multiple customers, but without using carrier grade NAT. So A+P needs three functionalities to be working. A+P actually works again by sharing an address among multiple customers, and each customers only have a range of source ports available. So it does not have all the source ports, it only have a range of ports available, and this is how we can share a public address among multiple customers. So if A plus P is running on the host, no problem. The host knows that they don't have all the ports available, and we have no problem of breaking the end-to-end connectivity, for instance. So the end-to-end peer-to-peer capability of Internet is restored. Now, if the hosts are not running A plus P, it means that we must have A plus P running on a router which is going to do a translation, but again, this translation is not NAT translation. It is just to make sure that the traffic which is getting out of the site is only using the source ports which have been allocated to this site and not the other source ports. So this box must do this translation. This box must do the encapsulation, for instance, IPv6 in IPv4 in IPv6, for instance, 4RD, which is doing IPv4 in IPv6. And it may require some signaling. So the signaling is to avoid the manual provisioning. The manual provisioning for each site to configure each site for the source ports range which are allocated for the site. The first proposal used DV and GVPD, and there is no signaling. It is based on manual provisioning, so you must configure each site with the range of ports which has been allocated to the sites. But in the future, we can imagine that a signaling protocol like, for instance, DHCP may require not only an IP public address, but an IP public address plus a port range, so each site will only have a range of ports available, and this way we can have the same public address shared by many sites. So there are also small drawbacks because, for instance, a site may not have available the ports. If an application needs a particular port, it may not have these ports, but it has so many benefits compared to CGN that it does not have all the states to manage. It is not a single point of failures. You can track a user based on the ports and on the address. So it is also possible with double NAT, but it is so more difficult than with A plus P. With A plus P, it is so much more easier because you know that a site has this address and this range of ports for all time. It is not a dynamic translation when you have to keep logs and at what time, knowing that which port was actually used by this customer or this customer. So A plus P has many benefits because it does not have all the drawback of carrier grade NAT while allowing to share a public IPv4 address among multiple sites. So the first proposal at the IETF is actually based on DV, which is a stateless NAT 464, and which actually permit to share a public address using the source ports. I gave you a link here with a very interesting test which has been performed, and I really recommend that you take a look at this test because it shows very good results in a test in a large network which was simulating a service provider backbone, and it has shows very good results. So thank you very much. This is actually not an exhaustive list of all the transition tools, but the most important and the most popular tools were introduced in this presentation. If you need any more information, documentation, whatever, please meet me on my website on fastlaneus.com. There is a blog where I write a lot of articles and posts. So please come and meet me and ask any question, challenge me if you want, and ask me any question you want. I will be very happy to answer. Thank you very much, and bye-bye.